thanks a lot. So yeah, so let me share my screen. Start.
Perfect.
Yes.
The floor is yours. Thank you.
Thank you. Yeah, so if you remember, I mean, we first talked about how mathematics can, let's say, analyze deep learning techniques, and now we are in the regime where we use deep learning techniques for solving mathematical problem settings. Yesterday we talked about how inverse problems can be solved, and today we will look at partial differential equations. And Wienen already gave, I think, a beautiful talk in this respect, so you will see certain aspects also appearing here, but maybe sometimes also in a different light. And the key part about partial differential equations, and I think I already mentioned this in the beginning, why neural networks are actually that effective, because it's not clear why you need to use neural networks at all for it, because you have very sophisticated solvers, is that they are, for some reason, able to beat this curse of dimensionality. And so this will be also part of the lecture. So, I mean, if you think back, expressivity, that was our second lecture. What we saw is that deep neural networks there are at least as good as most classical approximation tools. So we compared it, for instance, with approximation by wavelets or shearlets and so on. But something even more striking is true. So if you go in the high dimensional regime to high dimensional functions, then neural networks are extremely good in this and often outperform classical methods. And so for some reason, they are able to beat what's called this curse of dimensionality, which usually hits approximation methods so that they, in a certain sense, deteriorate exponentially fast when the dimension increases. And so the question and the one main task also related to partial differential equations, how can we understand this and how can we analyze? So what is the curse of dimensionality? I mean, Wienen already gave a very nice introduction, so let me recap a bit again what this is. So it was basically introduced in a certain sense by Berman in 61, and so if you look at this square and you would like to sample it in a certain sense uniformly, so that there is, let's say, a certain distance, maximal distance between points, I mean, then here you would need 10 to 2 evenly spaced points. But now if you drive the dimension up, then you get an exponential growth in how many sample points you need. And so this is what's typically called the curse of dimensionality. It appears in various forms, for instance, numerical integration, combinatorics, function approximation, as you will see here, machine learning, and so on. Now, so that's a major problem if you go to really high dimensional data. And so here you see a very classical result, which sources in a very easy setting. So if you have, for instance, a one Lipschitz continuous function, let's call it f, and then you have some continuous approximation scheme, which has, let's say, p3 parameters, then you can lower bound the error which you make when you approximate this function f in this way, p2 minus 1 over d. Now, what one observes, and this we also saw in various instances through the lectures, neural networks usually deal with massive dimensions. So for instance, already in imaging sciences. So the MNIST database, there you have 28 by 28 pixels per image, but for normal images, this goes up to 1024 by 1024 pixels or even higher. So the dimension which neural networks need to deal with are actually massive. And so now, I mean, if you would like to approximate and let's say set this side equal to epsilon, and then ask how many free parameters you actually need to get an approximation accuracy of that type, I mean, then you see for an error of epsilon, I mean, here this goes up the exponent. So this is the problem which a neural network should face, but for some reason, neural networks perform in this high dimensional regime extremely well. And so the question is, I mean, how to unravel, let's say, this mystery and understand it. And I mean, I also refer to Wienen's talk, who gave a lot of insight in this direction. So This cannot be explained by classical approximation theory. I need to think of different, let's say, avenues how to approach this. And there are various ways people aim to attack this. I would like to show you here two, and then go to the area of partial differential equations. So the first is what is called the manifold assumption. So usually, as we also said, I mean, data is typically on some lower dimensional manifold. So even if you're in the high dimensional regime, you have something lower dimensional which is in the background. And for some reason, neural networks are able to sense this to a certain extent. So let's assume, I mean, I have a function which I would like to approximate by, let's say, a ReLU neural network where D is very large. But I would like to approximate it in a certain way. Let's assume I have a manifold which is in this X, which is D prime dimensional, and D prime is much lower than D. So I have a low dimensional manifold sitting in my space. And let's assume I have a measure which is supported on that, and then I measure the error in the LP of mu. So that's, in a certain sense, consistent with task, with prediction task, where the data is generated by a measure on M times R. And as we also said, in imaging sciences, you usually assume that natural images, or for instance, also in particular this MNIST database, so handwritten digits, are on some much lower dimensional manifold as this would indicate. Okay, so how can we approximate this with a neural network? So there's a very constructive, or there's a, say, a constructive way to achieve that, which was used also in several papers, and which then leads to a rate which only depends on the lower dimension and not on the larger dimension. So this approach is taken in various papers, and the way it goes is as follows. So first, you let's assume this is my manifold here. So you first basically need to get a correspondence between the manifold and some Euclidean space where you can talk about regularity and issues like that. So let's assume the manifold is compact. I can approximate it with open balls that cover this manifold, and then as it is custom in this theory, there are, I mean, tangent spaces, and so you have local projections, so maps from the manifold to this tangent space, which are diffeomorphisms. So you can move easily between the manifold and local tangent spaces. And so then, I mean, you can define regularity on the manifold of G by basically bringing it on this tangent space. So you have this correspondence, and that all happens locally. So you have these, what's sometimes also called charges, which locally map the manifold to a tangent space. And so that would happen in each of these open balls. Okay, so that's kind of very, very classic, very traditional. So now I can write my G in this way. So here these gammas move between the manifold. So these are these local projections, and the phi is a partition of unity, so that each time the support is in one of these open balls. Remember, they cover M. And then in a short form notation, I can write it in this form. And so, I mean, this gamma I is a linear map, so I can very easily mimic this by a neural network, just with one layer. But also these partitions, since I have ReLU activation functions, I can also approximate by, in a certain sense, networks of a fixed size. And so remember that since G is in CK, I mean, also these functions here are in CK, so I can also those approximate well, because there are results from approximation theory for neural networks that I can extend those to a function on this space X, and then I can approximate it with a neural network of this size. Okay, good. So, and now, I mean, you see my G can be decomposed in this way. I can approximate this and this and this part. I can approximate the sum by a neural network through properties of neural networks. And so then I can assemble my finite neural network, which now approximates G. And if I count all the dimensions, I see that only D prime each time appears. So in that sense, I get a rate of D prime. Yeah, so that's what's, that's in a certain sense, one explanation people bring that neural networks can, let's say, be approximated in high dimensional space with a rate which is much lower. I mean, if you have this manifold assumption. Okay, so that's basically one way to view it. So another way is by random sampling. And so this is something which actually touches now the closest Winans talk, because he also talked a lot about barren spaces. And here I would also like to show you one of the instances is the first result. And then, I mean, Winan also pointed out where people went from that point on, but I think it's interesting to look also at maybe a bit more detailed now at this very early result, which also gave one instance of one early instance already that neural networks are able to beat the curse of dimensionality. Yeah, so here, I mean, my activation function is again a ReLU or also a sigmoidal function. I assume, or sorry, the theorem says there exists a constant so that for every, well, D and N and every measure supported on a ball and every G. Now, G is a bit special. It's an L1 function, but it satisfies this condition where this is the Fourier transform. Yeah, so the integral over the absolute value of the Fourier transform times the norm of xi is finite. Then I can approximate this G with a neural network, and the approximation rate is, you see, the N only appears and not the D. So this is a result which shows that you can approximate functions, presumably also high dimensional functions, which satisfy some natural condition with neural networks, but the error does not depend on D, on the dimension, but only on N. No? Okay, so N is here the number of neurons. Good, so I mean, you can replace this L2 approximation error also by an infinity approximation error, but let's not go too much into the details there. So now how do you prove such a result? So this random sampling will come into play at some point. So, and you also need to use that this CG is finite. So what you do in rough terms, since it's a sketch of the proof, is you look at this expression here. So this G is what you would like to approximate. It's just a constant, but then you can write it in this way, yeah, because I mean G of 0 is just the integral over G hat of psi. Yeah, so this inverse Fourier transform, and the G you can write as G hat, and then apply also the inverse Fourier transform. So then you can bring in this norm, you can bring in the CG, and you can combine everything by declaring this to be a probability measure. Yeah, and this is finite, that's the condition on G. So then comes, let's say, this random sampling idea. So then one can show that this expression, which we have here, can be written in this way. So you see the exact value for a certain function applied to random variables. And this function, which you see here, has this shape. So what you observe is that this is either -1 or 1. And you see here each time the characteristic function, which later on can be easily approximated by a neural network. And then you see here these inner products. Okay, so I can express this in this way. So I get the randomness into play there. And now, so this was my random variable. I take a realization. And so now I can show that the expected value of the norm reference of G to this expression. Yeah, and you see this expression before, if we go back. Yeah, so here we had this expected values. Now here we take the average over these, so it's like discrete mean of the of the function applied not to this realizations. And so then this arrow I can bound in this way, where now you see only the n appears and not the d. So here you get this rate which you actually aim for, and so then you get a realization so that the L2 error is of this order. Now once you have that, then you need to show next that neural networks can approximate this function actually. So this part. But this can be done. As I said, this function consists of characteristic functions of 0 infinity. These can be approximated by ReLU activation functions. And then from that, you can get an approximation of the entire function and gamma, and so that leads to this rate n to the -1/2. Yeah, so here basically you go through this random sampling to get then this approximation rate which you want, namely one which is independent on the ambient dimension and only depends on. So that's another instance of how to unravel this mystery why neural networks behave that well. It's actually a very old result, like you said, Thorne 92. That is already ancient. In this field. And so then, where people went was there are generalized Barron spaces, and so 1 and Ö just told you about where, from this point on, what you could do with it, which type of impressive results you can get these days. Yeah, so these are instances to analyze the course of dimensionality without at this point going into the PDE world. So now let's bring this, get this into play and approach partial differential equations. So again, let me stress, if you look at partial differential equations, they are rigorous physical models. So it is not clear why you actually would need deep learning, because the discretization process is usually very well understood. You often have optimal solvers, for instance, for elliptic PDEs. So there, you have finite elements for elliptic PDEs. You have this, for instance, optimality results for wavelet-based approaches, and so on. So the big question is, why do we need deep neural networks? And that's exactly, the point, that neural networks seem to be able to beat the course of dimensionality in high-dimensional problems, and there are already some rigorous results which prove that, and so that makes them that interesting in this regime. Yeah, because otherwise, there would be a question. This area is already very old. It has a lot of very sophisticated approaches. Yeah, but here, neural networks really have an edge. And so, one very, very common approach, which you also saw just 1 hour ago, is if you have a partial differential equation, you have here the differential operator, you have the right-hand side, then what people do is, solving means computing the solution. So you approximate the solution by the neural network. And then if you train this neural network, you will incorporate the PDE in the loss function. And there are various approaches which follow this this idea in different directions. So partial differential equations is a huge area. Each type of PDE needs to be dealt with differently. You have elliptic PDE, you have hyperbolic PDEs, parabolic PDEs, and so on and so on. What I would like to do now, I would like to take you in the world of parametric PDEs. So this is even a bit more general. You don't have just one partial differential equation, but you have a whole family of partial differential equations. And so there are certain, let's say, new types of questions come up beyond what I just showed you on the previous slide. So parameter-dependent families of PDEs, they appear basically everywhere, for instance, in complex design problems where you have parameters, which, for instance, indicate certain model parameters, the shape, or also parameters like the heat for the material and so on. And so the number of parameters can be finite, it can be also infinite. It makes it much more difficult. So here in our case, the number of parameters will be always in the finite region. And what is key here is the following. So let's take a look here. We have again the differential operator, we have the right hand side, but now you see this y is one parameter from my parameter space y. And so everything depends now on this parameter y. The right hand side depends on it, the solution depends on it, and well, I mean the y is also here, maybe in a other non-trivial way involved. And certainly what you aim for now is for each parameter y, you would like to compute the solution. And that's called the parametric map. You have a parameter, and for that parameter, you want to compute the corresponding solution. And this you might need to do multiple times, which then creates its own problem. But let's be a bit more specific. So we'll look at now this variational form. So here you have again the right-hand side. You have here, as its custom, a bilinear form applied to u, y, and v is from here. Okay, so let's be a bit more specific. So my my parameter set is in Rp. P can be extremely large, so that's the high dimension I'm facing. Let's assume it's compact. I have a Hilbert space. I have this By, which is a symmetric, universally coercive, uniformly continuous bilinear form. So these terms, I mean, if you're familiar with the area, it will tell you something. If not, I mean, it doesn't matter. Then you have the right-hand side, which also depends on y. This is, as I said, parameter dependent. It's uniformly bounded, and uy is the solution. And so there's another technical assumption, because you see, I mean, as you let your parameter y move, your solution will move through some space, to some manifold. And so this is the solution manifold, and we assume here it's compact. And so later on, remember, we had this manifold assumption already in the beginning of the talk. Later on, to some extent, I mean, one can show that neural networks seem to be able to sense the solution. Okay, so what do we need to do? As I already said, I mean, one might need to compute this parametric map multiple times. So you have each time a parameter from your RP, and you need to compute the solution. So as I said, this could be model parameters and so on. And so the curse of dimensionality could lead to the fact that the computational cost is extremely high. And the question is, do you want to use neural networks for this? How can you use them? Do they beat the curse of dimensionality here and so on? But first, I would like to show you what classically, I mean, one does to solve this problem. So first of all, I mean, remember we're in a Hilbert space. Now, if you want to have a chance to compute, you need to bring things down to the finite dimension. So I go now first from my Hilbert space to a finite dimensional space, which I call UH, and H stands for high fidelity discretization. And capital D is the dimension of this very high dimensional still space. And so again, I have this equation, which I need to solve for UYH. And so there's this famous Sears lemma, which says that this solution is the best approximation to UY, so which is the true solution, the continuous Hilbert space by elements in UH. So that's very nice. So if you solve this, you get best you can do in this finite dimensional space. So how do you solve this? Well, I mean, you just take a basis for your space. You plug the spaces in here, so you expand every of those elements in terms of your basis. You use that this is bilinear, so you pull the sums out, and in the end, what you get is that the solution UYH has this form, so you can write it in terms of your basis, and the coefficients have this shape. Now here, this comes from the right-hand side, Fy of phi y. So if you apply phi y here, if you expand this in phi y, and then here you have this matrix, so-called stiffness matrix, where again here you have this yi and yj, which came from when you expanded this in the base. So you can write exactly down, that's the so-called working solution, what form this has, and if you can compute this, you get the solution. Okay. Good. So now in this high dimensional space, in this RD, the parametric map looks like this. You want to map y to this coefficient sequence. Now, go back to this coefficient sequence in RD, so that this equation is satisfied. And so what I would like to ask now is the question is, can a neural network approximate this parametric map? Now, so that's a very general question. And what do we mean by this? And what do we expect and hope for? Well, first of all, if we can do that, I mean, we will get a neural network which extremely fast computes for each new set of, or for each new parameter, my corresponding coefficient vector. I have a very flexible approach, and hopefully it also beats then the cross of dimensionality. And so the question I want to ask is, first of all, does there exist a neural network at all which approximates this? So this would be phi from y. Yeah, so this is a question in the area of expressivity. And then how does the complexity of phi depend on P and capital D? Yeah, so what we certainly do not want is that it depends exponentially on it. Yeah, so this is testing theoretically whether the neural network is able to beat this curse of dimensionality. Then, so this is an existence result. Then, I mean, you can ask, now I train my neural network. So what happens then with the neural network I've trained? And certainly one would love to also have a theoretical result in this direction. But unfortunately, this seems to be still out of reach. So instead, one can then also numerically test the trained neural networks. And one sees there as well that those, even the trained ones, not only the constructed ones, even the trained ones beat the cross of dimensionality. Good, so there are, I mean, various approaches, as I said, and also Wine showed already, various, let's say, references. In particular, interesting for us are concerning parametric PDEs. And now let's see how we can tackle this theoretically first. And what we would like to do, this is almost the same slide as you already saw. We are aiming now for ReLU neural networks. You can also take other activation functions, but here we want to aim for taking these type of activation functions. So let me also at this point say what people have done before. Yeah, because there are some similarities. So there is what's called a reduced basis method, and this does the following. So again, I mean, let me say these UIs are my solutions in this continuous Hilbert space. Yeah? So let's assume this is my solution. Then, as we said, we go to the high fidelity discretization. We make a little error, and so this dotted line now is my solution set in my finite dimensional space. Yeah, so these are denoted, if you remember, by UYH. And then the key idea of this reduced basis method is that you take what's called snapshots. So for certain parameters, you compute the solution, and then you basically approximate if you have a new Y. Yeah, so that's in a way a key idea. And you see, I mean, there's a certain correspondence also to learning type methods, because you see also for learning type methods, you will need some training data. Yeah, so you could even view this as some sort of training data. So let's, I mean, this reduced basis method, again, let's look at a bit the details there, because, I mean, some of these components will appear in a moment. So now I go again a space down. I take now a reduced basis space where the dimension now is much smaller than capital D, which was my dimension for my high fidelity discretization. So this is now a really tiny space, and I call this dimension d of epsilon. Yeah, and what I would like is that the solution can be very good approximated by this space. So even if I look at the worst parameter, I will always find for the true solution an element in my little space which has just the distance of epsilon. And so there's a whole theory of that, how that could be achieved. So, okay, so now I transfer everything to this reduced spaces. So let's assume now I have, now remember I had my high fidelity space and now I have this reduced space. This basis I call psi. And so I can transfer things from my high fidelity basis to my reduced basis. So the transformation matrix I call V. And I can bring everything down, so I can also bring down the stiffness matrix and the right-hand side each time by multiplying with the transformation matrix. And then, I mean, I can also look at the solution in this reduced space in a very similar way as we saw before. I expand this solution in terms of my basis from my space. This gives me this coefficient vector. Remember, the dimension of the tiny space is d of epsilon. I can write this now in terms of the larger basis, of the larger space. And so this brings this transformation matrix in here. And then I can use what I already know from the Galerkin solution, that this is always the stiffness matrix inverted times the right-hand side. And so I get that my reduced basis solution has this form. And so this is sorry hard to see. This is the basis from the large space. And so what one can then show is the following. So let's first just take a look here. So one can show there exists indeed a ReLU neural network of this size, and what you observe immediately is that the d, the high fidelity dimension, appears just linearly, and the tiny dimension cubically, and the p also polynomially, so you don't have any exponential dependence. So this shows that the size, the complexity of the neural network does not suffer from this curse of dimensionality. And so this neural network satisfies what we expect. It approximates this solution, this coefficient vector from the solution in this high fidelity space by an epsilon for all parameters. But there are certain conditions which need to be satisfied. I mean, the first condition is basically the condition which always holds, I mean, which is always assumed. For instance, if you use this reduced basis method, so that this term, and let me go back, so this term is exactly this term, which is the coefficient vector of the solution, is close to the true term in the high fidelity space, so there exists such a stiffness matrix, so that this is close. And moreover, another condition is that there exist ReLU neural networks, so that here for the forward matrix, not for the inverse, which is later on used, but for the forward matrix, and for the right-hand side, the neural network approximates these terms up to epsilon of a certain size. This seems to be a quite strong condition, but it's actually not. I mean, it's something which is satisfied by various classes of PDEs. And so then, I mean, you can also show it in some sense for, say, discrete version, so where you look at specific Hilbert spaces and also show there with certain additional assumptions, where here you need that the neural networks approximate this, the basis of the reduced basis space very well, that also there you can get such a result, again, with a benign dependence on all the dimensions involved. And so these hypotheses are fulfilled for various different types of partial differential equations. So how do you prove such a result? As I said, it's a result in expressivity, and these results, as we also discussed, are always constructive. So you explicitly usually construct a neural network with certain properties. And what will play a tremendous role here is this term, which we already saw, that's the coefficient vector of the solution of this reduced basis solution. And so we've mainly show that this can be approximated by real neural networks. And then we use theory from the PDE to show that this can be actually, then the neural network approximates the solution. So how can you approximate this by a real neural network? And each time, certainly, you need to control the size, or the complexity. And this follows ideas which we already discussed. Yeah, so the first, remember, we discussed this idea by Jarodsky, how you can actually approximate, how you can approximate the square function by a neural network. And so this is exactly a recap from what we discussed there. So here you have these functions g, which you combine, and then you can express the x squared as this sum. And so this g, I should say this g, I mean, these are these head functions. So this is what we discussed, and now the g I can write then in this way. So I can express the square function because I can do that. I can also express scalar multiplication. So just by this formula, you see here, you just need a neural network for mimicking the square function, and then this is just an affine linear operation and a scalar. And so if you count things together, you can then show that scalar multiplication can be approximated by a neural network of this size. So in each step, you control the size. So now you can do scalar multiplication. If you can do that, you can also multiply matrices. So again, you can multiply matrices with that many scalar multiplications. That's not the best you can do. If you know work by Schoenberg and so on, you can get less, but it's sufficient for our purposes. So again, you can control the size of that. Then you need to do inversion. So you need to be able to invert matrices. This you do by a von Neumann series. So all of those, because you can do multiplication, you can approximate. And so then you can use that this converges to this inverse. And so using those ideas, you can then show that matrix multiplication can be approximated by neural networks of this size. And then you can get to the two results where you now use the assumptions that neural networks can approximate this stiffness matrix in a, let's say, nice way, and also the right-hand side. So that means this map can be approximated by a neural network of, again, a certain size. So each time you need to keep track of the complexity. And so then you can show these two results by using that here. Also this transformation matrix you can approximate. And so that way you get in a very, very constructive way. And if you look at the proofs, it's extremely technical and there are a lot of details in, but that way you can show that you can get neural networks which approximates these solutions, and you can keep track of the complexity. So that's what you can there do on the theoretical side. But as I said, certainly one, so that's an expressivity results. Neural networks exist. It doesn't mean if I train them that everything stays the same. And ideally, as I also said, one would like to certainly also prove things for the optimization procedure, generalization, if one now trains networks. But right now, in this sense, it seems still to be out of reach. So now let's look at some numerical experiments, because then the idea could be to analyze numerically how neural networks do for this task concerning curse of dimensionality. So we have these approximation theoretic explanations, and so the goal we aim for is to analyze how this theoretical effect, which we just proved, whether we can actually see this also in the performance of the learning problem. And so one certainly need to be aware of that this this result. So we have these upper bounds, whether they are really tight. We would like to analyze whether the optimization and the sampling, which we now need to do, because now we need to train the neural network, whether this somehow destroys the results. And also, these results are often asymptotic. So the question is, can we then see this when we now train the neural network? Can we see these effects even there if we just train this one instance? Okay, so what is always a problem in numerical analysis is how to compare tests in a fair way. Because now we would like to do an extensive test setup to be able to really, in various different settings, analyze whether through training this effect of beating the cross of dimensionality shows up. But we would like to do it in an optimally fair manner. And so problems with this is always, I mean, that you might sample differently, and it's hard to compare. The optimization procedure might kick in, and people might use different optimization procedures in different ways, and that also makes comparability of tests difficult. And also it's often not clear, I mean, you have some intrinsic complexity how you can quantify it. So what we do, I mean, in this whole experiments, which I will show you now, I mean, the architecture is always the same. It's one fixed architecture, no matter how we change the parameters and how we change the setting. We will analyze the convergence behavior a posteriori to give also, let's say, a better comparability. The sample generation will be, I mean, independent, and we will have a lot of very, let's say, carefully designed test cases, which are, as it says, semi-ordered, and you will see that. Now, if you drive experiments, what you always should do, certainly, is you start with some hypothesis, which then you hope you can prove or you can disprove. And so the hypothesis here, which we set up, was the performance does not suffer from the cross of dimensionality. The performance is very sensitive to parameterizations, the various ways to parameterize, and also learning is efficient also for non-affinely parameterized problems, which are usually extremely difficult with classical methods to handle. And so there are also various related studies, but in different settings and not in the setting which we set up here. But let me just say, I mean, there are a lot of other experiments in this direction. Okay, so that's our setup. We take this diffusion equation. So we have here the parameter. It's defined on the unit square, and on the boundary we have 0 as a condition. And so these AY are the diffusion coefficient. We will say in a moment a bit more detail how we actually define that precisely, because that will be the parameterization where we want to check how sensitive things are. So the parametric map, as we saw, is we have a Y, we have UY, and we want to do that for various choices of parameterizations. So what we will do and what we will vary the type of parameterization, the dimension of the parameter space, so it's P, and also, as we will see, the complexity of the hyperparameters. Okay, so a bit more detailed. Again, that's our parametric diffusion equation. So now this A is our the parameter. Now, so here, I mean, this we now define as A. So the A is something in A, so that would be these AYs. The right-hand side is this function, and the parameterization will have different forms. Yeah, so these parameterizations, these AY will be of that form. You see the Y coming up here, so and this is in RP. And now the question is, what is this A0 and what are these AIs? And so there you can certainly choose various different settings. So the sequence AI, there are numerous possibilities to choose. And so here are a couple of what we chose, and which is very traditional and classic in this area. We can choose trigonometric polynomials, so-called chessboard partition, which looks like this, cookies with fixed radii and with variable radii, and also so-called clipped polynomials. And one typically distinguishes between so-called affine parameterizations and non-affine parameterizations, where these being much more difficult and usually also very difficult to handle by classical methods. And so that's the setup, which will now be the same for all experiments. We have, this is our space where we work on. We have 101 times 101 equidistant grid points. That's not a lot, but I mean, also the training takes some time. So therefore we use such a, let's say, a bit coarser sampling. We always use this network. Yeah, so the output dimension need to be 101 squared to get a value for each of those points. Input dimensions P, and the middle layers are all 300. We have 11 layers. We have this activation function, so-called leaky ReLU. We always use the same number of parameter samples. We initialize always in the same way. The loss function is always the same, and optimization is exactly the same procedure. The dimension varies up to 91, which is already, I mean, it doesn't sound a lot, but in that area, it's already a huge dimension. And so these are now some numerical experiments. First, I mean, in the affine regime. So here you have this trigonometric polynomial. What you observe here is the parameter dimension, which grows. And here you see the test error, but what you see is that you have a more or less linear behavior here. So you don't get any exponential dependence on the parameter dimension. Yeah, and it's the same for this chessboard partition, still in the affine regime. Again, you get this linear behavior, and what is also really nice to see is that the training is actually really benign. So I mean, you have a very, very nice training curve. Then cookies with variable radii. So this is now the non-affine world. And again, I mean, you see, if you look at this picture, again, you see this kind of linear behavior. And again, I mean, the training goes down very nicely. So apparently, I mean, the network doesn't really care that much about these different parameterizations, in that sense that still you have this behavior that it doesn't depend in a bad way on the dimension, and also some of the training is benign. So one can say, I mean, we showed that the first hypothesis is true, at least in that sense numerically. The performance does not suffer from the cross of dimensionality. That is true. Is very sensitive to parameterizations. Yes, I mean, there are strong differences, but I mean, each time you don't have this cross of dimensionality appearing. So in a certain sense, what we could also in a certain sense find out, which I didn't discuss here in much detail. I mean, if you look at these intrinsic dimensions, that seems to be a major factor for determining the hardness. And I mean, learning is also efficient for these non-affinely parameterized problems, which are in real world really hard. So that is also true, which is actually very nice. I mean, it shows the potential of these methods as opposed to classical methods. And so let me conclude. So here, I mean, we live in this high dimensional regime because their neural networks are extremely effective. Usually that is actually a problem, this cross of dimensionality, but it's still, I mean, to a certain extent, we have now very interesting results which show already to a certain extent why neural networks are able to handle this cross of dimensionality, but still, I mean, there's a lot of space and space to fill concerning this mystery. What I showed you here were, I mean, this manifold assumption, which gave us a bit of insight, this random sampling. And then we went into the world of PDEs. Here in the world of parametric PDEs, so this very general problems where you have a family of PDEs parameterized, and what we showed were you can get upper bounds on the complexity of radio neural networks to approximate such parametric maps, and this theoretic bound is not depending on the cross of dimensionality, or let's say it doesn't show because of dimensionality. We then went in the numerics world and showed that there also from a numerical standpoint, the training is benign, and then also the neural networks which you get from training do not suffer from the cross of dimensionality. And so let me stop here, and let me also mention, since there was a question about, let's say, survey papers and introduction into the areas, I mean, this is also something you could take a look at. I mean, some parts of these lectures are also contained in there. So this gives also maybe to a certain extent an overview of some of the newer approaches. And with this, I'd like to close, and thanks a lot for your attention.
Thank you very much, Gitta, for the very nice talk. So we have now time for questions. Yes, please.
Yes, thank you for this very interesting talk. And I mean, the results of approximation of random networks for the high fidelity solution are remarkable. And I have two questions actually. The first one is it possible that random networks can well approximate the high fidelity solution because somehow they manage to create some sort of multivariate spline approximation of the solution? I mean, for their architecture. I mean, and I was taking this connection from the isogeometrical analysis.
Yeah, so that's a very interesting question. Thanks for that. Yeah, we know that, I mean, splines are actually very effective for approximating solutions here. I mean, one need to say that, I mean, this result can be also extended to other activation functions. So in a certain sense, yeah, I mean, there's an advantage of ReLUs to use, but I mean, you can also use different activation functions. So it's not, I mean, the result is not solely restricted to ReLUs, and in that sense to, let's say, the spline viewpoint. Okay, and the second question is, I mean, as I read in many papers, the reduced order models carried on by neural networks are yes, fast in the test phase, but very computationally expensive in the training phase. And I want to ask in which context or applications this drawback could affect significantly, and if there are also directions to overcome this issue. So yeah, I mean, the connection was one time not that great. So you were saying that, I mean, for reduced basis, these methods are... I mean, no, I mean, the training phase is computationally expensive related to the test phase. And so I was asking if, I mean, how to overcome this issue, and how this could affect, I mean, in which context or application this issue could affect significantly. Yeah, so okay, so to compare with this reduced basis method, so there, yeah, so you have these two phases for reduced basis method. You have this offline phase and the online phase. The offline phase also takes a long time, and then the online phase is faster. So that's comparable to what you do with neural networks. You have the training phase, which also takes some time. I mean, depending on how many training samples you use, which accuracy you want. And then once you have the neural network, it's extremely fast because these neural networks are not deep. And so then, I mean, the computational cost is extremely low, let's say, on the side when you then apply it. Now, I mean, certainly, yeah, so the training phase, you cannot get around how to improve this. Yeah, so that's a difficult question. I mean, it might be that if you're a bit smarter in choosing your training samples, but then you need maybe a bit more knowledge on your PDE. So that's anyhow something, I guess, which is maybe a bit underestimated in the whole area. I mean, how to choose actually the training samples. Maybe you don't want to choose them IID, you would like to choose them in a different way. And here you have a PDE, you have much more knowledge. So maybe you could do something also smarter in that direction. Okay, thank you very much.
Some more questions here. Well, maybe I can go for another question that is regarding about at what extent actually holds your results. For instance, when you introduce your parametric setting, or you mentioned that you are working strictly on symmetric coercive settings. So what happens, for instance, in the non-symmetric, non-coercive setting, for instance, and second of all, how your results holds and is dependent on the properties of the network itself. Like for instance, you consider a particular family of networks, but there are more complex one in real world, like ensembles and so on, how that affects actually your results.
You mean the theoretical results or the numerical results?
Yeah, first the theoretical results regarding about the setting, that is happens and extension of non-symmetric, non-coercive. Have you considered that? Doesn't seem trivial to do the extension.
Yeah.
Yeah.
So yes. So for the first question, I mean, you're absolutely right. I mean, so these conditions are crucial. I mean, it could be that you can go beyond that, but I mean, so we don't have any results in that direction yet. So right now, I mean, so this is the setting. It's still a fairly large setting, as I showed. I mean, most diffusion equations and so on are contained in that. But you're right. I mean, one need to go beyond that. I mean, there are maybe some results also by Philip Petersen in that direction. But yeah, so there's a lot of, let's say, potential for improvement. Now, concerning the architecture, I mean, for theoretical analysis, we explicitly, so as I said, construct neural networks. So it's these are very special neural networks which then come out of the theory. For the numerical experiments, so this was the setup we chose. Certainly, I mean, again, there's a lot of room for doing different, using different types of networks. So in that sense, I mean, what I showed you, I can say for these type of networks, how things behave. It could be that for other types of networks, also with more layers or so on, I mean, things are even better. But so this is, let's say up to maybe also other groups to do more experiments in that direction.
And from a theoretical point of view, doesn't affect actually the result, because maybe the characteristics on the height, the width, and so on are actually can be included there, and you can reach actually not the optimal result, but as optimal. So it's from the practical and theoretical point of view. Yeah.
So as I said, I mean, from the theory, we get just one network out, because it's exactly constructed. I mean, you're asking if can you now use, I mean, if I understood you correctly, for the theory, networks of different width and different number of layers. I mean, the question we asked there was a question of expressivity. We just wanted to have one network which did this approximation task. You can then certainly, I mean, next ask, I mean, can you reduce the size? Can you reduce the complexity? That could be, I mean, also, for instance, I mean, if you remember the proof, I mean, in matrix multiplication, we used this algorithm which gave us D2 2. So you can also bring that down. So if you are much smarter in the proof in each step, you can get in the theoretical results also networks of, let's say, lower complexity, but not of the order of complexity. So here we were just interested in the order of complexity. We were not interested in the constants. But if you want to bring that down, I mean, then you can do, and you can be much more sophisticated in the proofs as well.
Okay, thank you. So do we have more questions? Let's see, I think in the chat we have questions. So Gitta, we have a question in the chat. Can you please take a look about it?
Yes, so maybe you can read it. I mean, it says, regarding the transformation matrix Y, the theory shows its existence, or can we really find it? Any assumptions on V? Do they affect the approximation capability of neural networks? So this transformation matrix Y came up when we said, I mean, we find a reduced basis space. So certainly, I mean, this depends on the existence of such a reduced basis space. Once we have that, I mean, then we can find an orthonormal basis for the space. we have an orthonormal basis for the large space, and then we have this transformation matrix. So then, I mean, so this all depends on whether we find such a reduced basis space, and there are numerous results in the area of PDEs which show that under certain conditions this can be done. And so for that, I mean, we don't put any assumptions on V. The assumptions, as you saw, I mean, were on the existence of such a reduced basis.
Yep. Thank you. So do we have more questions here? If not, I would like to thank again Gitta for the amazing talk. Thank you very much.